Hello everyone. Today we'll present the paper Firmware: Automatic Detection of Authentication Bypass Vulnerabilities in Binary Firmware, written by researchers at UC Santa Barbara. My name is Rafael Montalvo and my teammates are Wyatt Dowley and Roberto Perez, and we are Group 19. So, before diving into details, let me give you a quick roadmap. I'll start by explaining the background, why embedded device security is important, and what problems exist in firmware today. Then I'll define the problem statement, what exactly the authors wanted to solve. And after that, I'll introduce the solution they propose, called Firmware. My teammates will then continue with the implementation details, evaluation results, limitations, and future work. By the end, you'll see how this paper connects to real-world security issues in devices that many of us use every single day. Okay, so let's start with the embedded devices. Well, let's think about our daily life. How many devices around you run firmware? Well, we have the Wi-Fi router at home, and a smart lock on a door, security cameras, printers in office, and even smart meters that track your electricity use. These are all examples of embedded devices that rely on firmware to function. Firmware is the built-in software that tells the device how to operate. Unlike apps on a phone, firmware isn't easy to update or inspect. It's low level and often hidden from users. The important point is that as these devices spread everywhere, from homes to hospitals to power grids, the attack surface grows enormously. Each device is a potential target if its firmware has weakness. But why firmware security matters? Well, these devices don't just handle a small task. They deal with sensitive or critical data. For example, a hacked smart meter could leak information about when you are at home or away, just by analyzing your power usage. Or a compromised smart lock could allow someone to open a door without your knowledge. And even in corporate environments, network printers could be abused to steal sensitive documents. So, this isn't just a theory. In 2014, a massive incident happened with Linksys routers. Attackers found a way to bypass authentication and hijack over 300,000 devices, creating a huge botnet. This shows that firmware vulnerabilities can scale to hundreds of thousands of victims at once. So, protecting firmware isn't just about one device. It's about protecting entire networks and even critical infrastructure. Let's talk about the types of firmware vulnerabilities. Firmware can suffer from many types of vulnerabilities. Some examples are memory corruption, where attackers override memory to control execution, or command injection, where crafted input makes the device run dangerous commands. And the focus of this paper, authentication bypasses, also known as backdoors. Authentication bypasses are especially dangerous because they undermine the most basic security measure, which is logging in. If authentication can be bypassed, then all other protections collapse. So imagine having a safe with a very strong lock, but someone secretly left a second key taped under the door. That's essentially what a backdoor in firmware is. Let me explain authentication bypass more clearly. Normally, when you try to do something privileged, like change router settings, you must enter the right username and password. But in some firmware, the code may contain a hidden check that allows anyone with a specific hard-coded value to pass. This means attackers can log in without ever knowing the real credentials. Sometimes this happens by accident because of poor coding practices, and other times manufacturers deliberately insert these bypasses for maintenance, thinking nobody will notice. In both cases, the end result is the same. An attacker gains unauthorized access, which can lead to full control of the device. And why detection is so hard? Well, the challenge is that firmware is often a black box. Unlike normal software, where you can read the source code, firmware is usually distributed as a binary blob, a large compiled file with no documentation, no comments, and no clear structure. On top of that, many devices require firmware to be cryptographically signed, so you can't modify or test it easily. Each manufacturer also uses different architectures and custom code, making it even more complex. Because of these obstacles, most existing methods either don't scale or they require physical access to the device. And what about manual analysis? Well, that's slow. It can lead to error-prone and is simply not feasible. So here's the research gap the authors identified. They need a solution that can analyze binary firmware directly. No source code, no access to the physical device, and the solution has to be scalable. So it works not just for small programs, but also for complex firmware with thousands of functions. And most importantly, it has to be automatic. This is the space where the authors propose their system called Firmalism. Firmalism is the first automatic framework designed to detect authentication bypasses directly in binary firmware. It's significant because it doesn't need access to the actual device or its source code. That makes it practical for analyzing a large number of devices. Think of Firmalism as a kind of X-ray machine. For it can look inside and identify suspicious paths and tells whether a bypass exists. All of that without needing the original blueprints or access to the actual hardware. The key idea behind Firmalism is called input determinism. In simple terms, it asks one question. Can an attacker figure out the exact input required to perform a privileged operation just by analyzing the firmware? If the firmware itself contains that information, for example, a hard-coded password, then the authentication is bypassable. This concept helps firmalists distinguish between normal authentication checks and hiding backdoors. It's not just looking for strings. It's analyzing whether inputs are deterministic from the program perspective. And how does Firmalism achieve this? Well, the process works like a pipeline with three main steps. The program slicing, where it cuts away irrelevant code and focuses only on the parts related to authentication, reducing complexity. Then the symbolic execution, where instead of running the program with actual inputs, it explores all possible paths symbolically, considering inputs as variables, and the constraint solving, where finally it checks whether those variables can be concretely determined by an attacker. If yes, the system flags it as a bypass. Here's a very simple example from the paper to show us what is a backdoor. So the firmware had code like this. If the username equals go and the password equals on, then return success. This means anyone who enters go and on will be authenticated, regardless of what the real credentials are. Firmalists was able to detect this automatically because those values are deterministic. They come directly from the firmware itself.
Hello, everyone. We will continue our presentation on from Alice and go over the overview of the implementation. Firm Alice represents a breakthrough in automated firmware security analysis built on sophisticated foundation of symbolic execution program slicing techniques. What makes this system particularly powerful is that it operates directly on binary firmware, eliminating the dependency on source code availability. This is absolutely critical because the vast majority of commercial firmware is proprietary and closed source. Manufacturers rarely provide access to their underlying code. Multi, multi, uh, multi-architecture support and technical innovation. The architecture supports ARM, PowerPC, and x86 processors through an elegant intermediate representation approach. Instead of building separate analysis engines for each for each processor family, which would be enormously complex and resource intensive, the researchers developed a translation layer that converts binary code from different architectures into a unified intermediate form. This abstraction allows consistent analysis across different hardware platforms while maintaining the semantic accuracy necessary for reliable vulnerability detection. The intermediate representation preserves critical details like memory, access patterns, and control flaw structures, and data dependencies that are essential for security analysis. Component architecture deep dive. The firmware loader handles the complex challenges of extracting and preparing firmware-bound binaries for analysis. Modern firmware comes in dozens of different packaging formats, some compressed, some encrypted, some embedded within larger system images. The loader implements sophisticated format detection algorithms and extraction routines that can handle proprietary packaging methods used by manufacturers like Cisco, Netgear, and Link System, and various industrial device makers. A static program analyzer performs the initial vulnerability identification phase through advanced pattern matching and control flow analysis. It constructs comprehensive program models, including function boundaries, call graphs, and data flow relations. This static analysis phase is computationally efficient and creates a solid foundation for major resource-intensive symbolic execution that follows. The symbolic execution engine represents the core technological innovation of Firm Alice. Unlike traditional dynamic analysis that executes code with concrete inputs, symbolic execution uses symbolic variables to represent inputs and can explore multiple execution paths simultaneously. The engine maintains complex path constraints and uses constraint solvers to determine which execution paths are actually feasible under real-world conditions. This approach can discover vulnerabilities that occur only under very specific input conditions, vulnerabilities that might never surface during normal testing or operation. The Authentication Bypass Checker implements domain-specific analysis patterns tailored for embedded device authentication mechanisms. It recognizes common authentication patterns like challenge response protocols, token-based systems, and credential verification routines, then applies targeted symbolic execution to systematically search for bypass connections. Performance and scalability considerations. The system implements several critical optimization strategies to handle the computational complexities inherent in symbolic execution. Path pruning eliminates infeasible execution paths early in the analysis phase. State merging combines similar symbolic states to reduce memory consumption. This system also employs guided exploration heuristics that prioritize analysis of code regions most likely to contain vulnerabilities based on historic attack patterns and vulnerability databases. Evaluation on commercial firmware. The researchers conducted comprehensive evaluation on 3 carefully selected commercial devices, each representing different embedded systems categories with distinct security requirements and threat models. Detailed device analyst results. The Schneider Ion A6000 smart meter critical infrastructure vulnerability. This industrial power monitoring device processes critical infrastructure data and connects directly to SCADA network that control power grid operations. Firmware analysis revealed multiple severe security flaws. That system contains hard-coded administrative credentials embedded directly in the firmware binary, passwords that could never be changed by system administrators or users. Most troubling, the analysis discovered a hidden telnet interface accessible through undocumented network ports that bypassed all normal authentication mechanisms. The symbolic execution phase undiscovered that the most serious vulnerability, a complete authentication bypass mechanism triggered by specific command sequences. When certain malformed network packets were sent to the device, the authentication verification function would return success regardless of whether valid credentials were provided. This type of logic flaw is extremely difficult to detect through traditional testing because it requires precise knowledge of internal authentication algorithm implementation. 3S Vision N5072 network CT camera surveillance system compromise. The network security camera analysis revealed even more extensive vulnerabilities. Formalis discovered multiple hard-coded passwords providing different levels of system access, including maintenance credentials that granted full administrative control. The firmware contained active debugging interfaces that were never disabled in production builds, creating unintended attack vectors that completely bypass normal security controls. The authentication bypass vulnerability discovered in this device were particularly sophisticated. It involved a buffer overflow condition in the credential parsing routine. Then, when triggered with precisely formatted input, this overflow would cause authentication function to return success without validating credentials. This vulnerability demonstrates why automated analysis is so valuable. Specific input formatting required to trigger these flaws. This formality demonstrates why automatic analysis is so valuable. Basic input formatting requires triggers. This flaw would likely never be attempted during normal testing usage. Dell 1130N laser printer success implementation security implementation success. The Dell printer presented the positive example of this evaluation. Despite thorough analysis, firm Alice found no significant authentication bypass vulnerabilities or hard-coded credential issues. The firmware demonstrated proper input validation throughout the authentication subsystem, avoiding hard-coded credentials entirely and following secure coding procedures consistently. This provided that secure embedded firmware development is absolutely achievable with certain technology and established security practices. FirmOS performance and accuracy metrics. FirmOS achieved extremely 82% reduction in annual analysis time compared to manual reverse engineering approaches. Tasks that previously required days or weeks of expert analysis time can now be completed in hours. For concrete comparison, the standard smart meter firmware analysis that required 3 to 4 hours of manual reverse engineering work was completed by firmware in just 4.8 hours, including vulnerability configuration, initial exploit development guidance. System 83 analysis detection rate significantly surpasses manual analysis capabilities. This superior performance occurs because automated symbolic execution can systematically explore execution paths that human analysis might overlook, skip due to time constraints, or simply miss due to complex of modern firmware. Manual analysis tends to focus on obvious vulnerability patterns and common attack vectors, while automating analysis while automated analysis can discover subtle logic flaws buried deep in complex interaction.
Good evening. My name is Roberto Perez, and I will continue with this presentation. Welcome to my presentation, FirmWise, which is a tool designed by the UC Santa Barbara researchers to automatically detect authentication, bypass vulnerabilities in binary firmware. This is critical as embedded devices like smart locks, and meters, sensors, so many different IoTs there that have grown globally and quickly. This is very important because all these embedded devices with firmware, they have flaws posing privacy and security risks, which it could impact security. I'll cover this those approaches and limitations and future work and FirmWise, and we'll open it for questions if I had everyone from, but I'm pretty sure we will cover a lot of information that we'll cover about FirmWise. Well, the next slide, we will talk a little bit about the approach and overview and the challenges and future. So on the approach, let's talk a little bit about how the FirmWise as a fascinating tool is tackling a big problem in cybersecurity, which is it analyzes all the information that is aligned or is embedded on devices like printers, cameras, but unlike applications, a source code is often locked away. That means that it's tough to check the security and flaws of each one of those firmwares. FirmWise steps in by loading the firmware and parsing its security policies. Those are the rules that say what operations are restricted. So as a programmer or software engineer, having limited access to this firmware is very difficult to access the sensitive functions and also determine how secure or unsecure could be these firmwares. But FirmWise then uses techniques called symbolic execution with something called like input determinism model, which in simple terms, it just simulates a possible input. An attacker may try to sneak past those restrictions. But actually, what is the goal by doing this? Well, it's a find bypasses ways an attacker could trick the system into granting access to locked down features. Let me give you an example. It's like Firmware tested devices like a network printer, a smart meter, and a CCTV camera. Well, it found explorable backdoors in 2 of them. Think about hard-coded passwords or hidden interfaces that shouldn't be there, but they are. This is huge because manual analysis, where experts digging through the code by hand, is way too slow for the millions of devices that are out there. Like I mentioned before, like sensors or any of these, a lot of the devices are now the functionalities and the IoT or Internet of Things. By automating this process, firmware saves times and catches vulnerabilities that could otherwise be missed. But let me explain it this way. It's like having a super smart detective for your device's firmware, keeping them safer from cyber attack. It's pretty cool, right? But that's how firmware is changing the game in secure Internet of Things, which is everywhere. IoTs are everywhere. Now, in the next slides, we're going to talk about, and actually, I'm on that slide right now, on limitations and future work. Despite of its promises, Thermalize has limitations, defining security policies, and manually is time intensive and error prone. Just imagine like a manually has to define every single one of those policies for each one of those devices. It struggles with large binaries and binary blocks, lacking standard formats, and automation is limited, which is relying on analysts on input. Hardware specific quirks like undocumented initialization also poses challenges. Looking ahead and the future work could automate policy inference to save time, but it will also improve scalability and loading methods which would handle complex firmware better. But let's talk a little bit more about this. First, defining security policies is a major hurdle. These policies specify restricted operations and firmware, like accessing sensitive functions by inputting them manually is incredibly time consuming, as I mentioned before, and prone to errors. Imagine an analyst painstakingly mapping out every single one of the rules for complex devices software. It's like assembling a puzzle with half the pieces missing. Next, Firmware struggles with large binaries and binary blobs, as I mentioned before, because chunks of those codes that lack standard format. This can be massive and disorganized, making analysis slow and very difficult. But it's like it's trying to read a book written in a jumbo language. Automation is another issue. Firmware isn't fully automated. It relies heavily on analyst input to guide process, as I said before, and this dependence it slows down things as analysts must constantly steer a tool. It's adding to that hardware-specific issues like undocumented initialization process. Is thinking about all the mess around that. Without knowing this, Firmware can hit a wall like trying to unlock a door without having the right key. Now, looking ahead, how we can improve Firmware? Well, as I stated before, automating policy inference will be a huge enhancement. Instead of analysts manually defining rules that could learn, if they can learn themselves, it will save hours of efforts. And also scalability is also a key. Enhancing a Firmware handles large, complex binaries, and blobs will also make it more efficient for modern devices. And finally, expanding the scope of about Firmware and the way how things are doing or are done recently is exciting. Right now, Firmware focuses on finding bypasses like backdoors or hardcore credentials, which is part of what we're expecting all the improvement being made. To wrap up, Firmware faces challenges, as we say, like time consuming for those manual policy input, and also struggle with those large binaries. So in conclusion, Firmware is a game changer for security firmware, especially as smart devices like cameras, printers, and all those devices. They and they are everywhere nowadays. So with that conclusion, that this is the end of my presentation, by automating the hunt of these flows is helping keep our devices safer and increasingly connected age. With that said, Firmware is not perfect. It has limitations as I stated before in my presentation. I'm not going to repeat all those limitations. I already said it twice, but it's important that we keep that in mind. So with that said, thank you for your attention. I'm excited about where Firmware is headed. And if I had the team here in front of me, I'm pretty sure there would be a lot of questions. So I do hope all this information is beneficial. Thank you.